So for our last section in Chapter 9b, we're going to talk about geometric probability. Hopefully you remember from your previous math classes that when you're dealing with probability, the set of all possible outcomes of an experiment is called our sample space, and any set of outcomes is called our event. So if every outcome in the sample space is equally likely, then we know the probability, or the theoretical probability, of the event occurring is where you take the number of outcomes in that event and you divide it by the number of outcomes in our sample space. That'll make a little bit more sense when we take a look at a couple examples. So our examples then, we're taking a look, we're going to deal with different types of models. Sometimes we're going to deal with length of segments, sometimes we're going to deal with angle measurements, and sometimes we're going to deal with area. So if I'm working with length specifically, let's take a look at segment AD here. The sample space that we're working with, so all possibilities, are all the points that would be sitting on our segment AD. I might then take a specific event and say, hey, I would really like to know what the probability is of a point sitting on segment BC. So that would be my event. To find the probability, you take whatever your event is, the possible number of outcomes that you would have for your event, and divide it by the possible number of outcomes you would have for your sample space. Hence why the probability of having a point sit on segment BC would be to take the length of BC and divide it by the length of AD. In the case for our angle measurements, if we're dealing with something like this in a circle, if I look at it, the sample space is going to be all of the points in our circle. The event would be all of the points that specifically sit in the shaded region here. So if I want to know what is the probability that I would have a point sitting in the shaded region, I would take the angle degree measurement for this shaded region and divide it by 360 degrees. The last possible model is the area model. So if I talk about the sample space, we're going to deal with the whole entire sample space, the whole entire rectangular area. I'm interested in what is the probability of a point sitting in the shaded triangle, so that would be my event, all the points in my triangle. The probability would be the area of the triangle divided by the area of my rectangle. So let's take a look at this example. In this example, we're dealing with geometric probability dealing with length. And we've got a point, and we're going to choose a point that is going to be randomly situated on our line segment PS. And we're going to find the probability at each of these three possible events. So the first thing before I get started, I know that I need to figure out, it's nice that they've labeled PQ and QR and RS for me, but I do know that I want to figure out what the length of PS is. So quickly, if I take 7 plus 13 plus 5 and I add it all up, I know the length of my segment PS is going to be 25. That'll end up being extremely helpful for us later on because that is our sample space, because that's all the points that's in our line segment. So for the first one here, it says the point on RS. So I want to know, what is the probability that if I were to pick a point on PS that it would lie on RS? Well, our event is the points on RS, and our sample space is the whole entire PS. So our RS is 5 units, and our sample space is 25 units, so I would take, the probability would be 5 over 25, which if I reduce that down would end up giving me 1/5. So my probability of a point sitting on segment RS is 1/5. Next one, it says the point is not on QR. Well, let's take a look. What does it mean to be not on QR? Well, here's QR. If the point was not to be on QR, it would either have to be on PQ or it would have to be on RS. So I know that the probability of it being on PQ, since its PQ is 7, the probability of being on PQ would be 7 over 25. And I have the possibility of it sitting on RS, and the probability of it sitting on RS would be 5 over 25. So if I add those two up, because it was not on QR, I would end up getting 12 over 25. So the probability of it not sitting on QR would be 12 over 25. So for our last example, we want to take a look at when the point is on PQ or on QR. Now, the probability of it sitting on PQ, we said, would be 7 over 25. And the probability of it sitting on QR, if we take a look specifically at that one, would be 13 over 25. So if I add those two together, we're going to end up getting 20 over 25. And 20 over 25, I can pull a 5 from both. And when I pull a 5 from both, we are left with 4/5. So for our next example here, we have the angle measurements, and we're going to figure out, using a spinner, the probability of each of the following events are going to be. I'm going to do the first one with you, and then I'm going to let you loose on the other two on your own. So the first one says we're going to find out what the probability of the pointer landing on yellow would be. Well, yellow here is this whole entire space. Now this whole entire space has a 140-degree angle. So the probability of the spinner landing in here, we said with the angle degree measurement, you're going to take the probability of the event occurring, which is 140 degrees, and divide it by the 360 degrees we have in a circle. Now, I can take a 10 away from each of these, so cross the zeros out, and then if I simplify down by taking a 2 out of each, I'm left with 7 over 18. So the probability of it landing on yellow would be 7 over 18. How about you go ahead and try the next two on your own, pause the video, and when you're all set and ready, start it up again, and I'll have the answers written for you. Okay, so taking a look at B, it says the pointer landing on blue or red. Well, blue has an angle degree measure of 52, so the probability of it landing on blue would be 52 over 360. Red has an angle degree measure of 60, so it would be 60 divided by 360 for the probability of it landing on red. So if we take those two probabilities and add them together, I get 112 over 360, and I pulled an 8 out of both of those to simplify it down. Make sure you're always simplifying your probabilities down. And I ended up getting 14 over 45. For the last one, the pointer not landing on green, well, I know there's 360 degrees in every single circle that we're working with. So if there's 360 degrees in a circle and I don't want it to land on the green area, I ended up taking 360 minus 108. That would give me everything else. Otherwise, what you could do is you could take 60 plus 140 plus 52. You'd still get 252 divided by my 360, and then all you do is simplify down. And when we simplify down, we're going to pull a 36 out of each, and I'm going to get 7 over 10. So for our last example that we're going to work through in this set of notes, it says we're going to find the probability that a point chosen randomly inside of my whole entire rectangle here actually sits in my circle. So the event is finding the point to sit in the circle, and the whole sample space is my rectangle. Now we're talking about areas. So when I set up my probability problem, I would say we want to find out what the area of the circle is, and we're going to then divide that by the area of my sample space, which is my rectangle. Now, for those of you who don't remember, the area of a circle formula is pi r squared, and the area formula for a rectangle is length times width. So why don't you go ahead and do me a favor, pause the video at this point in time, try to find the area of the circle on your own, along with the area of the rectangle, and when you're done with that, you're going to go ahead and actually round that fraction off. Put the fraction in the calculator and round it to the nearest hundredth. When you're set, start the video up again, and I'll have my answer written down for you. So taking a look at my work, I ended up saying that with the area of the circle, it was pi r squared. So I know this distance here is 18. Radius would then mean it would be a 9 for my radius. Plugging that into my formula, I get pi 9 squared. The last thing, area of my rectangle, it was 50 units by 28 units. So I took those two and multiplied them. So I have 81 pi over 1400. If you throw it in your calculator and round to the nearest hundredth, the probability of you getting a point to sit inside of the circle compared to the whole entire rectangle is going to be 0.18. If you have any questions regarding the probability, make sure you write them down and you ask in class. Have a great night.